If I was to ask you what the square root of negative 9 is, that's a problem because there is no real number that you can square to get negative 9. You might think it's negative 3, but if you square negative 3, if you take negative 3 times negative 3, that's 9. Or since it's not negative 3, you might think it's positive 3. Well, if you square positive 3, if you take 3 times 3, that's still 9. So there is no real number that you can square to get a negative 9. That's why these complex numbers were invented. Complex numbers are based on a number whose square is negative 1. So when you're dealing with imaginary numbers or complex numbers or taking the square root of a negative number, there's just two simple rules you have to remember. I squared equals negative 1 and I equals the square root of negative 1. The imaginary unit I is the complex number whose square is negative 1. Just two simple rules. And if you remember one, you can get the other. If you remember that I squared equals negative 1, then take the square root of each side and you would have I equals the square root of negative 1. Or if you remember that I equals the square root of negative 1, square each side and you would get I squared equals negative 1. Square root of a negative real number. For any positive real number a, so if we're taking the square root of negative a, what you can do is break that into the square root of negative 1 times a. And up here it says the square root of negative 1 is I. So you could split that into the square root of negative 1 times the square root of a. And the square root of negative 1 is I. That would be I times the square root of a. So that can be worked with. That can be simplified. The square root of negative a can be simplified into I times the square root of a. Here's another way to think about this. If you square the square root of negative 5, that should turn out to be negative 5. So that should simplify to be negative 5. Well, you can break that into the square root of negative 1 times the square root of 5, and that's still squared. The square root of negative 1 is I, so that would be I times the square root of 5 squared. And remember, we should get negative 5 for an answer. Now, if you square each one of those, everything inside the parentheses, if you square that, I squared and the square root of 5 squared. Well, I squared is negative 1. So that would be negative 1 times 5, because if you square the square root of 5, that is 5. Remember, we should be getting negative 5, and that's what we have. Negative 1 times 5 is negative 5. So once again, two simple rules to work with complex numbers, imaginary numbers, taking the square root of negative numbers. These two rules, I squared equals negative 1, and I equals the square root of negative 1. How do you write the square root of negative 18 in simplest radical form and using the imaginary unit I? Well, the square root of negative 18, first you can break that into the square root of negative 1 times the square root of 18. Remember that square root of negative 1 will turn out to be I. But that square root of 18, that can break down into the square root of 9 times the square root of 2. So the square root of negative 1 is I. The square root of 18 splits into the square root of 9 times the square root of 2. And the square root of 9 is 3, so that would end up being 3I times the square root of 2. So to simplify that square root of negative 18, that turns out to be 3I times the square root of 2. We'll take a look at these three. The square root of negative 12. You can break that down into the square root of negative 1 times the square root of 12. Remember, the square root of negative 1 is I. And the square root of 12 will break into the square root of 4 times the square root of 3. We're splitting that square root of 12 into two factors where one of them has a perfect square root. So break the square root of 12 down into the square root of 4 and square root of 3. That 4 is a perfect square. That has a perfect square root. So the square root of 4 is 2. That would turn out to be 2I times the square root of 3. Next, the square root of negative 25. You can split that into the square root of negative 1 times the square root of 25. And the square root of negative 1 is I. The square root of 25 is 5. So that would just be 5I. And finally, the square root of negative 7. You can break that into the square root of negative 1 times the square root of 7. And the square root of negative 1 again is I. So it would be I times the square root of 7. A little known fact is how to graph a complex number. In the complex number plane, the point AB represents the complex number A plus BI. To graph a complex number, locate the real part on the horizontal axis, so the real part of the complex number goes on the horizontal axis, and then locate the imaginary part on the vertical axis. So if we're graphing the point 3 minus 2i, we're going to graph that complex number. The real number part is 3, and the imaginary part is negative 2i. So the real part, 3, you're going to the right 3, and the imaginary part, negative 2, you're going down 2. So yes, it's just graphing the point 3, negative 2. Go to the right 3 and down 2. That is the graph of the complex number 3 minus 2i. The absolute value of a complex number is its distance from the origin. So if we're going to find out how far that point is from the origin, that's getting the absolute value of that complex number. And to do that, you see a right triangle is formed. Where you go to the right 3 and down 2, that right triangle has legs of 3 and 2. Now everybody knows the Pythagorean Theorem, and that's what we're going to use to get that distance from the origin. So with legs of 3 and 2, remember the Pythagorean Theorem is a squared plus b squared equals c squared. We're going to take 3 squared plus 2 squared equals c squared, where 3 and 2 are the legs of that right triangle, and the hypotenuse is the distance from the origin. We're finding the hypotenuse, which is really finding the absolute value of 3 minus 2i. In real numbers, absolute value is the distance away from 0, and with complex numbers, it's the distance away from the origin if you're looking at it graphically. So 3 squared plus 2 squared to be 9 plus 4 equals c squared, 13 equals c squared, and then take the square root of each side, c equals the square root of 13. So that hypotenuse, that distance from the origin, is the square root of 13. In other words, the absolute value of 3 minus 2i is the square root of 13. So a little known fact there, and a couple things that might get you a point on the ACT test, you never know, is how to graph a complex number. Just graph the real number part, that's the x coordinate. The imaginary part, that's the y coordinate. So you go to the right 3 and down 2. That's the graph of 3 minus 2i. And then the absolute value of that complex number is its distance from the origin. And to get the distance that point is from the origin, set up a right triangle. You're finding the hypotenuse with the Pythagorean Theorem. That gives you the distance that is from the origin, which is the square root of 13. So the absolute value of 3 minus 2i is the square root of 13. What are the graph and absolute value of each complex number? Starting with negative 5 plus 3i. Remember to graph that. The real part, the negative 5, that's the x coordinate. And the imaginary part, the 3i, that's the y coordinate. So simply go to the left 5 and up 3. If you go to the left 5 and up 3 and put a point, that is the graph of negative 5 plus 3i. Now to find the absolute value of that, you would be finding how far it is away from the origin. Think of taking the absolute value of a real number. You're finding out how far that number is away from 0. Here we're finding out how far that point is away from the origin. So imagine a right triangle is created there where you have legs of 5 and 3, and you would be finding the hypotenuse, the distance away from the origin. So use the Pythagorean Theorem, a squared plus b squared equals c squared, where a and b are the legs, in this case 5 and 3. You'd have 5 squared plus 3 squared equals c squared. That's 25 plus 9 equals c squared. 34 equals c squared. And then take the square root of each side. C equals the square root of 34, where c is the hypotenuse, in this case the distance away from the origin, which is the absolute value of negative 5 plus 3i. So the absolute value of negative 5 plus 3i is the square root of 34. For 6i, it's pretty easy to graph that. There is no real part showing, but you could always put a 0 in. Just go up 6 on the y-axis. So the 0, that's the x-coordinate. You're not going left or right any. 6i, that'd be the y-coordinate. Just go up 6. So just go up 6, put a point. That is the graph of 6i. Now to find out how far that is away from the origin, or finding the absolute value of 6i, real simple. You just went up 6. So the distance away from the origin is 6. And lastly, 5 minus I, to graph that. The real part, that's the x-coordinate. Just go to the right 5. And the imaginary part, that's the y-coordinate. Go down 1. So go to the right 5 and down 1. That is the graph of 5 minus I. Now to find the absolute value of that, you're finding out how far that is away from the origin. So imagine that right triangle is created where you have legs of 5 and 1, and use the Pythagorean Theorem. So take 5 squared plus 1 squared equals c squared to be 25 plus 1 equals c squared. 26 equals c squared, and then take the square root of each side. C equals the square root of 26. So the distance away from the origin, the hypotenuse of that right triangle, would be the square root of 26. And that is the absolute value of 5 minus I. Absolute value of 5 minus I is the square root of 26. We're going to add and subtract complex numbers. It's real simple. Think about what you do when you have x's and y's involved. Some rules are going to be the same here. If we have 5 minus 3i minus a negative 2 plus 4i. You need to remove the parentheses, distribute that negative sign through that second set of parentheses. So take the negative of a negative 2, it's positive 2, and the negative of a 4i, that is negative 4i. So we have 5 minus 3i plus 2 minus 4i. And then go back and combine the like terms. So negative 3i, negative 4i, if you combine those, that would be negative 7i. And 5 and 2 is 7. So you end up with 7 minus 7i. Now when you write your answer, you want to put the real part first, the imaginary part second. So don't write this as negative 7i plus 7. People might make fun of you. Write it as 7 minus 7i. With the real part first, the imaginary part second. If you have 7 minus 2i plus negative 3 plus i, take out the parentheses. Nothing is going to change here when you take out the parentheses as far as the signs go because you have a plus sign between those parentheses. So it'd be 7 minus 2i minus 3 plus i. Go back and combine the like terms. You have negative 2i and I, also 7 and negative 3. So if you combine 7 and negative 3, it's 4. Negative 2i and I, that is negative I. Again, final answer should be in the form of a plus bi. So you want to write that as 4 minus I instead of negative I plus 4. 1 plus 5i minus 3 minus 2i. Watch your signs. When you take out the parentheses here, distribute that negative sign through that second set of parentheses. It's going to be the negative of 3, it's negative 3. And the negative of negative 2i, that is 2i. Go back and combine the like terms. 1 and negative 3, that makes negative 2. And 5i and 2i, that is 7i. So it'd be negative 2 plus 7i. 8 plus 6i minus 8 minus 6i. Take out the parentheses. Distribute the negative sign through that second set of parentheses. So that'd be negative 8 and plus 6i. And then combine the like terms. 8 and negative 8, that's 0. 6i and 6i, if you combine those, that is 12i. So that would just simplify to be 12i. And finally, negative 3 plus 9i plus 3 plus 9i. Again, with a plus sign between the parentheses, nothing will change as far as the signs go when you take out the parentheses. It's negative 3 plus 9i plus 3 plus 9i. Combine the like terms, negative 3 and 3, again, that makes 0. 9i and 9i, that is 18i. Multiplying complex numbers, very similar to when you're multiplying with x's and y's. Just remember those two rules I said at the beginning. I squared equals negative 1, and I equals the square root of negative 1. You multiply complex numbers just as you would multiply binomials by using the distributive property or the FOIL method. So here we have 3i times negative 5 plus 2i. We're going to use the distributive property there. Distribute the 3i through that set of parentheses. 3i times negative 5 and 3i times 2i. Then go back through and multiply 3i by negative 5, that is negative 15i, and 3i times 2i, that is 6i squared. Remember, I squared is negative 1. So 6 times I squared is really 6 times negative 1. So negative 15i minus 6. We're going to write that in the proper form, put that real part to the front. So that negative 6 gets moved out to the front. It's going to be negative 6 minus 59. Make sure you carry that sign that's in front of that 6. Carry that negative sign with it. Negative 6 minus 59. 4 plus 3i times negative 1 minus 2i. Here we're multiplying two binomials. So we're going to use the FOIL method or distributive property. Remember, when you're multiplying two binomials, the FOIL method and the distributive property are really the same thing. I'm going to take 4 times negative 1. We're distributing that 4 to that second set of parentheses. So 4 times negative 1, what you know as the first terms of the FOIL method. Then distribute the 4 to the negative 2i, which you know as the outer terms of the FOIL method. Then 3i times negative 1. Those are the inner terms of the FOIL method. And distribute the 3i to the negative 2i. Those are the last terms of the FOIL method. 4 times negative 1, that is negative 4. 4 times negative 2i would be negative 8i. 3i times negative 1 is negative 3i. And 3i times negative 2i, that would be negative 6i squared. You got like terms you can combine in the middle. Negative 8i, negative 3i, that makes negative 11i. Also negative 6 times I squared, that is negative 6 times negative 1. Remember, I squared is negative 1. So that negative 6 times negative 1 on the end, that would be a plus 6. So we have negative 4 minus 11i plus 6. Combine the like terms, negative 4 and 6, that makes 2. It'd be 2 minus 11i. We're going to multiply negative 6 plus I and negative 6 minus I. So distribute the negative 6 to that second set of parentheses, or what you know as the first and outer terms of the FOIL method. So negative 6 times negative 6 and negative 6 times negative I. Then distribute the I through that second set of parentheses, or what you know as the inner and the last terms of the FOIL method. I times negative 6 and I times negative I. Multiply through that. Out front, negative 6 times negative 6 is positive 36. Then negative 6 times negative I is positive 6i. I times negative 6 would be negative 6i. And I times negative I, that is negative I squared. Look to combine the like terms, and also remember I squared is negative 1. So 6i, negative 6i, that makes 0. Those knock each other out. I squared is negative 1, so that would be minus a negative 1. Watch your signs there. Minus I squared is minus a negative 1. 36 minus a negative 1, that'd be 36 plus 1, and that is 37. Next, 7i times 3i. If you multiply those together, 7i times 3i, just multiply the 7 and 3, it's 21. And the I times I is I squared. Remember, I squared is negative 1. So 21 times I squared is the same as 21 times negative 1, and that is negative 21. We're going to multiply negative 4 plus 5i and negative 4 minus 5i. So if you multiply those, FOIL method or distributive property, it's the same thing when you're multiplying two binomials. Distribute that negative 4 to that second set of parentheses. So negative 4 times negative 4, those would be the first terms of the FOIL method. And negative 4 times negative 5i, those are the outer terms of the FOIL method. Then distribute the 5i to that second set of parentheses. 5i times negative 4, those are the inner terms of the FOIL method. And 5i times negative 5i, those are the last terms of the FOIL method. Multiply through that. Negative 4 times negative 4, that is positive 16. Negative 4 times negative 5i is positive 20i. 5i times negative 4 would be negative 20i. And on the end, 5i times negative 5i is negative 25i squared. Combine the like terms in the middle. 20i and negative 20i, those two will knock each other out. That's 0. On the end, negative 25 times I squared, that's going to be negative 25 times negative 1. Why? Because I squared is negative 1. Negative 25 times negative 1 on the end, that would be a plus 25. So that is 16 plus 25, and that is 41. So when you multiply negative 4 plus 5i times negative 4 minus 5i, you actually get a real number, 41. This product is a real number. When you're multiplying number pairs of the form a plus bi times a minus bi, those are what are called complex conjugates. So this negative 4 plus 5i times negative 4 minus 5i, notice the terms are the same in each binomial. The only difference is the sign between the terms. So the negative 4's are the same, the 5i's are the same, the difference is the plus and the minus sign. That's in the form of a plus bi and a minus bi. When you multiply those together, you get a real number. Those are called complex conjugates. So the product of complex conjugates turns out to be a real number. Keep that in mind. We're going to be using that in a little bit. For an expression to be simplified, you cannot be left with an I in the denominator. It's just like radical signs. When you simplify an expression with radical signs, you cannot leave a radical sign in the denominator. So we can't leave this I in the denominator here, the bottom. That is not simplified. So to get rid of that I from the denominator, you have to think about what could you multiply the top and bottom by so that that denominator changes into a real number. Well, you know that I squared equals negative 1. So if you somehow make that into 3i squared, that would turn into 3 times negative 1. So the question is, what do you multiply by to get that? I. Multiply the top and bottom by I. Whatever you do to the bottom, you have to do to the top. Think about an equation. Whatever you do to the left side, you have to do to the right side. Same thing with fractions. Whatever you do to the denominator, you have to do to the numerator. So you have to treat them both equally. So we're multiplying the top and bottom by I. In the numerator, I times 9 is 9i, and I times 12i, that is 12i squared. And in the denominator, 3i times I, that is 3i squared. Remember, I squared is negative 1. So wherever you see an I squared, change that to negative 1. So it'd be 9i plus 12 times negative 1. And then 3i squared, that is 3 times negative 1. 12 times negative 1 in the numerator, that is negative 12. And 3 times negative 1 in the denominator, that is negative 3. So we have 9i minus 12 all over negative 3. But think about that. All of those are divisible by 3. So what you could do is think of dividing 9i by negative 3 and the negative 12 by negative 3. So if you divide negative 12 by negative 3, that's 4. Remember, the real part goes out front. If you divide 9i by negative 3, that is negative 3i. So completely simplified answer here is 4 minus 3i. Remember, for an expression to be simplified, you cannot be left with an I in the denominator. And if you think, well, we'll just do it like the last one where we multiply the top and bottom by I, you're wrong. Because if you take that bottom by I, the problem is not with the 4I. That would turn into 4I squared, and that I would disappear. The problem is out front with the 1. So if you take that bottom by I, it's going to turn into I minus 4I squared, which would be I plus 4. So you would still have an I left in the denominator. A couple of problems ago, I talked about multiplying complex conjugates in the form of A plus BI times A minus BI, and I told you to remember that. You need it here. So we need to multiply the top and bottom by the conjugate of the denominator. Well, the conjugate of the denominator is the same terms, just a different sign between the terms. So 1 minus 4i times 1 plus 4i, that's the key. Multiplying those two complex conjugates will end up being a difference of two squares, and it'll end up turning into a real number, as you will see. So we have to multiply the top and bottom by the conjugate of the denominator when you have a binomial or a complex number in the denominator that's a binomial, such as 1 minus 4i. So multiply the top and bottom by 1 plus 4i. We're going to use the FOIL method on top, so I'm going to skip over the whole writing out the FOIL method here. Take 2 times 1 is 2, 2 times 4i be 8i, 3i times 1 is 3i, so the 8i and 3i in the middle, that's where the 11i comes from. And then the last term's 3i times 4i is 12i squared. So 2 plus 11i plus 12i squared. Now the denominator. You could go through the whole FOIL method of distributive property, but keep in mind, multiplying two conjugates is going to produce a difference of two squares. So really all you have to do is square the first term, that's 1, square the last term, that's 16i squared, and then put a minus sign between them. It's just like if you have x plus 3 times x minus 3. That's x squared minus 9. Just square the first term, square the last term, put a minus sign between them. You've dealt with the difference of two squares before. Now wherever you see an I squared, that is negative 1. So on top, 2 plus 11i plus 12 times negative 1. And in the denominator, 1 minus 16i squared would be 1 minus 16 times negative 1. Watch your signs. 12 times negative 1, that is negative 12. And negative 16 times negative 1, that would be a positive 16. 1 plus 16 in the denominator is 17. And in the numerator, 2 and negative 12, that is negative 10. So that'd be negative 10 plus 11i all over 17. Notice the I magically disappeared from the denominator. So if we go back to the beginning, multiplying the top and bottom by I there would not cut it. You have to multiply the top and bottom by the conjugate of the denominator. So when you have a binomial with an imaginary number involved, you have to multiply the top and bottom by the conjugate of the denominator, which would be the same terms, just a different sign between the terms. That will simplify to be then negative 10 plus 11i all over 17. The I has disappeared from the denominator. Complex conjugates can be used to factor expressions. If we have a plus bi times a minus bi, don't need to write this down, just watch, and we're going to discover a little known fact. A plus bi times a minus bi, with the FOIL method of distributive property, take a times a, and then take a times negative bi. Bi times a, distributing the bi through the second set of parentheses, and bi times negative bi. So just FOIL method of distributive property there, no big deal. Multiply through that. A times a is a squared. A times negative bi is negative abi. Bi times a is abi. And bi times negative bi, that is negative b squared I squared. In the middle, combine the like terms. That is 0. A squared minus b squared I squared is what we're left with. Remember, I squared is negative 1, so it's a squared minus b squared times negative 1. Now this negative b squared times negative 1 will turn out to be plus b squared. So here we have a squared plus b squared. Now think about this. We've talked about factoring a difference of two squares. A squared minus b squared. That factors into a plus b times a minus b. Well, here we have a sum of two squares. We never talked about factoring that. A sum of two squares will factor because we just multiplied to get this. So this a squared plus b squared, that is a sum of two squares, and that factors into a plus bi times a minus bi. So a little known fact there is how to factor a sum of two squares. We know how to factor a difference of two squares, but we haven't talked about, and very few people know how to factor a sum of two squares. A squared plus b squared, that factors into a plus bi times a minus bi. That's where you want to start writing things down. 2x squared plus 32, we're going to factor that. Look for a common factor that you can factor out. You can factor 2 out of that. So if you factor 2 out, it's 2 times x squared plus 16. Now that x squared plus 16, that is a sum of two squares. You have two perfect squares with a plus sign between them. That factors, so it's in the form of a squared plus b squared. That factors into the form of a plus bi times a minus bi. Think about what that would factor into if it was x squared minus 16. If it was x squared minus 16, it'd factor into x plus 4 times x minus 4. Well, this will factor into x plus 4i times x minus 4i. So the factoring is very similar to if it was a difference of two squares. If it's a sum of two squares, you just attach an I onto those second terms. So the complete factorization there is 2 times x plus 4i times x minus 4i. Now you might be thinking there's no way that multiplies together to be this 2x squared plus 32. Watch. If you multiply those together, so 2 times x plus 4i times x minus 4i, you could use the distributive property or FOIL method, really doesn't matter. I'm going to distribute the 2 through that first set of parentheses, so 2 times x is 2x, 2 times 4i is 8i. Now we're going to multiply these two binomials together. You don't need to write this down. Again, just watch. I'm going to prove myself right. Multiply those two binomials together. Distributive property of FOIL method, 2x times x is 2x squared. 2x times negative 4i, that is negative 8xi. 8i times x would be 8xi, and 8i times negative 4i, that is negative 32i squared. Now combine the like terms in the middle, negative 8xi and 8xi, those will knock each other out. So we're left with 2x squared minus 32i squared. Remember, I squared is negative 1. So it'd be 2x squared minus 32 times negative 1. And guess what? Big surprise, that turns out to be 2x squared plus 32. So it is possible to factor a sum of two squares. In the form of a squared plus b squared, sum of two squares will factor into a plus bi times a minus bi. So this, factor 2 out first, and then the x squared plus 16 factors into x plus 4i times x minus 4i. We're going to factor 5x squared plus 20. Always look for a common factor that you could factor out. First, 5 is a common factor of those two terms. So if you divide each term by 5, that's what goes in the parentheses. Divide 5x squared by 5, it's x squared. Divide 20 by 5, that is 4. Now that x squared plus 4, that is a sum of two squares. It's in the form of a squared plus b squared. That factors into a plus bi times a minus bi. Easiest way to think about that is what would that factor into if it was x squared minus 4? It'd be x plus 2 and x minus 2. Well, this, a sum of two squares, factors into x plus 2i times x minus 2i. So the complete factorization there is 5 times x plus 2i times x minus 2i. If we have x squared plus 81, that is a sum of two squares. You have two perfect squares with a plus sign between them. Think about what that would factor into if it was x squared minus 81, a difference of two squares. It would factor into x plus 9 times x minus 9. Well, this factors into x plus 9i times x minus 9i. We're going to find the solutions of 2x squared minus 3x plus 5 equals 0. We're going to solve this for x. Now to solve this for x, we might try factoring by grouping, where we split this negative 3x into two terms. Their coefficients multiplied to get what 2 times 5 is. So they multiply to get 10, and they add to get this middle coefficient of negative 3. Well, that's a problem. There are no two numbers that multiply to get 10 and add to get negative 3. You can't proceed with factoring by grouping. It does not factor. So what we have to do is use the quadratic formula. Pick out a, b, and c. A is the coefficient of x squared, that's 2. B is the coefficient of x, it's negative 3. And c is the constant term, the number without a variable, that is 5. Quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So if you substitute those into the quadratic formula, take the negative of b, that'd be the negative of a negative 3, plus or minus the square root of b squared, that is negative 3 squared, minus 4ac, that is minus 4 times 2 times 5. All over 2a, which in this case is 2 times 2. Work through that. Watch your signs. Take the negative of a negative 3 out front. That's going to be a positive 3. Under the square root sign, if you square negative 3, it's 9. And watch your sign here. Negative 4 times 2 times 5, that is negative 40. In the denominator, 2 times 2, that is 4. 9 minus 40 under the square root sign, that'd be negative 31. So we're looking at 3 plus or minus the square root of negative 31 all over 4. Remember, when you take the square root of a negative number, we're going to split that square root of negative 31 into the square root of negative 1 times the square root of 31. The square root of negative 1 is I, so that would be 3 plus or minus I times the square root of 31 all over 4. So you have two solutions here, two imaginary solutions. 3 plus I times the square root of 31 all over 4, and 3 minus I times the square root of 31 all over 4. So you can still solve this for x. We're going to get two imaginary solutions. If you graphed this, it would not hit the x-axis. On the graphing calculator, you would not see it hit the x-axis. Since the coefficient of x squared is positive, this parabola opens up, and it would not hit the x-axis because you have two imaginary solutions.